Communication happens all the time, but then communication only makes sense when you can quickly deliver the information that you want to. Light does best in that. As you can see, light in free space can go anywhere it wants. In between generation and detection, can I use this light for exciting things? We want to tell the light where to go. So this is exactly what we do in our research group, developing photonic circuits and use light to do all kind of electronic signal processing and using optical signals.
The scientists in CeNSE are working on translating this world onto a chip, photonic integrated chip.
I have a requirement, right? So I want to change the polarization. But then the expertise is with the material scientist. So the material scientist can tell me what kind of material can do this.
They come back to us, tell us how we have to improve the properties of materials. We do that, give it back to them. They then make better devices. So in our group, we concentrate on establishing the materials platform required for developing such electronics. We work on oxide electronics, and we then work in collaboration with Professor Shankar Kumar Selvaraja's group, who take these oxide materials on wafers, and they make, instead of electronic circuits, they make what are called as integrated photonic circuits. And there again, we have a group of students who work jointly between Professor Shankar and myself.
At the one end, we have really low power photonics where we use, microwatts and milliwatts of power in order to make circuits out of photonics. But on the other end, we make kilowatt class, light emitters, particularly, fiber lasers.
So the other problem that we are looking at is how do you make lasers of very high power? Turns out such lasers have to be done in multiple modules and then put all together to make this one large beam. They only work at very specific wavelengths, and our goal is to make high power laser sources at a wide variety of wavelengths. And to do that, we utilize this nonlinear optics and an optical fiber, specifically cascaded Raman scattering. Technology, referred to as Raman lasers, is a field in which our group here at Center for Nanoscience and Engineering is among the leading groups in the world. We currently hold the world record in the highest power achieved from a Raman laser in the eye-safe wavelength region of 1.5 micron. So efficacy of a laser source arises from not just power, but the variety of colors or wavelengths that you have access to, right? And so that is a primary problem we are trying to address, which is how do I make these very advanced and very useful laser sources at an arbitrary number of wavelengths according to individual applications. So we work in the entire spectrum of optics.
So one can be used for doing very small, highly sensitive sensing. On the other end, with really high power lasers, you can do material processing, astronomical experiments as well. So there is a huge, scope that we have here at Center for Nanoscience.
So if you look at it, it has physics, it has electronics, it has materials engineering, it has mechanical engineering, and it has computational engineering. And
so the interdisciplinary nature creates an environment where all the fields are contributing towards a new generation of knowledge that everyone is trying to do better than what it is today.